In this lecture, we will analyze cross-coupled oscillator, and these oscillators are created from common source tuned amplifier. So first, we will study tuned amplifier. So when we talk of simple common source amplifier, we have a resistor here, and then MOS. Input is given here, output is taken at the drain. So this is simple common source amplifier. And this amplifier will amplify all the frequency components which are fed here. But we can make this amplifier amplify only one specific frequency by adding one parallel LC with the resistor. So here, earlier we had a load equal to R, but now we have a load consisting of all these three elements. So ZL now is parallel combination of R, C, and the L. So why we are talking about this load is that the gain, the voltage gain of this common source amplifier is given by minus GM into the load, and this is valid for lambda is equal to 0. So once we know the load, we can find out the gain. So we want to study this amplifier at certain frequency at omega naught and see that whether we can use this amplifier or what we need to do to convert this amplifier into an oscillator. Because we know that oscillator invariably contains one amplifier also. So here AV then becomes minus G M divided by 1 by R plus J omega C minus J by omega L. So we want to know that how this AV magnitude will vary and how the phase will vary, because if we want to create an oscillator, then we have to ensure the Berkhausen criteria. That means certain phase around the loop has to be formed and the phase requirement has to be fulfilled in addition to the loop gain requirement. So we will study this gain for three cases. One is when the frequency is very small compared with the frequency, what is called the resonance frequency. That means the frequency where this imaginary part is equal to 0. And that will give rise to omega is equal to 1 by LC. So let us call it omega naught. So first case, when the operating frequency omega is much less than omega naught. Or in fact omega is very close to DC. So in this case, what we see is that out of these three terms that we see here, this inductive term will dominate. This one will be the largest. So for this case, AV can be approximated as minus j omega L into Gm. And this can be written as minus omega L Gm e raised power j pi by 2 or omega L Gm e raised power j pi plus pi by 2. So here we see that the phase of the voltage gain is equal to 3 pi by 2 equal to 270 degree. And magnitude is omega L Gm. So this is going to be very small because omega is very small. Now for case 2, we consider the resonance frequency omega is equal to omega naught. So here for this case, what we get is AV is equal to minus Gm into R or GMR e raised power j pi. So for this case, the phase is equal to 180 degree and magnitude is equal to Gm into R. Now case 3, when omega is very, very large, so in this case, we can see that out of these 3 terms, this capacitive term will start dominating. So we can make approximation. So AV becomes approximately equal to minus Gm by G omega C. So this becomes equal to Gm by omega C. So that is Gm by omega C e raised power j pi by 2. So the phase is equal to pi by 2 and the magnitude is Gm by omega C, again very small. So now we can make the plot of magnitude and the phase of the voltage gain, AB magnitude. So here we see that he attains the maximum value for omega naught, and this is going to be equal to GMR. And regarding the phase, for the phase part, we see that it starts from maximum of 270 degree and comes to a minimum of 90 degree. And 90 degree occurs for the very large frequency and 274 small. So there will be change from 270 to 90, and this at the resonance frequency, the phase is 180 degree. So if you want to use this amplifier, then for making an oscillator, then we will have to do something so that we can get a total of 360 degree phase shift. Of course, by making a loop. So if we try to make the loop using this single amplifier, then we will not be able to achieve a phase shift of 360 degree, because here we can see that at max it is able to offer the phase shift of 270 degree. So we cannot make this loop and expect that there will be finite output for no input, because the maximum phase shift possible is only 270 degree, and that too at almost at DC. So we will rarely be using it at DC. And minimum is 90 degree. So even if you use two of such, we will not be able to get 360 degree at for large frequency. But at the resonance, it offers 180 degree phase shift. So there is a possibility that if we use another tuned amplifier, so we have one more tuned amplifier, and this is also going to offer 180 degree at omega naught, and the second one is also going to offer 180 degree, and both of course have same the load network. Then only they will be able to offer the resonance at the same frequency. So here there will be 180 degree phase shift from input to output, 180 degree from this input to this output. So total can become one, in fact, will be 360 degree if we interconnect them. That means output of the first to the input of the second, and output of the second back to the input of the first. So now if we make this loop, then there will be a total of 360 degree phase shift. So first input is V1, first output is V2, and the second output is V3. So here we see that V2 is going to be minus GMR, minus GM1. If we say this is M1, this is M2 into V1, and V3 is equal to minus GM2 R V2. So V3 in terms of V1 will be GM1 GM2 R square into V1 by multiplying these equation 1 and 2. So we get this. So here loop gain is equal to GM1 GM2 R square, and if we make this equal to 1, GM1 GM2 R is equal to 1, so it will fulfill one of the requirements of the Barkhausen criteria, that beta A should be equal to 1 magnitude, and the phase is anyway 360 degree. So there is a possibility that this circuit will oscillate. That means there will be non-zero output, this V3, even for zero input. So what will happen here is there will always be some thermal noise present in the circuit. That means there will always be some voltage. These voltages will be there. And then the frequency component at omega naught will be picked up, in a sense that for that frequency around this loop there will be a total of 360 degree phase shift. And if we ensure this equation 3, then in fact in the beginning we will have to, in the beginning this loop gain should be greater than 1, so that every time a signal completes one loop, it grows, its amplitude increases. So what will happen, that signal component at omega naught in the noise will start growing up gradually. So what we will have here is time varying sinusoidal output, and recall here that because inductor is connected between VDD and the drain, so the DC voltage at the drain of the both the MOS is going to be VDD. That means all these time varying voltages that we are going to see, V2 or V3, they are going to oscillate about VDD. So now if we show the plot of the output. So this is VDD level. So we can call these as Vx and Vy voltages. So if you see Vx and Vy, so initially it will be a small signal, but it will gradually grow out. And since Vx and Vy, they have 180-degree phase shift, because Vy is output of the M2 whose input is Vx. So obviously the Vx and Vy, they will have 180-degree phase shift. So what will be the Vy? The Vy will be like this. So this is how the signal will grow. So we will get a fixed value output after certain duration. So output will settle. So we find that this circuit uh, can act as an oscillator if we satisfy those criteria, uh, especially the magnitude criteria. The phase will automatically get satisfied. Now we can represent this circuit in a more compact form by combining these load networks, because you can see that these networks, they are identical, same components they have been used, and we are now going to reorient these M1 and M2 to create a more compact version, and that will also then illustrate why this circuit is called a cross-coupled oscillator. So this is oscillator, and cross coupling is present here. So we are now going to redraw it in slightly different way. So this is M1, and we have M2 here. So this, they have common source connected to ground. So what we found was the drain of the first MOS, which is V2, is given as input to the second MOS. So drain of first is connected in this way, and this drain of out second MOS, which is V3, is fed back to the gate of the first. So here, so now you can see that there is a cross coupling, one feeding to other feeding to the first one, and that is why this is called cross couple architecture. Now, what about these RLC? So here we see that the one of the ends of RLC, they are connected to the drain, respective drain, and other end is basically connected to same supply VDD. So other end can be short circuited with each of the respective values. So here we first see that a resistor is connected in this way. This is VDD. So this is R, this is R, and then capacitor is also connected in this way. These 2 points are VDD, and then finally the inductor here. So all these points are connected to VDD. So here we have L, L, C, C, R, R. And keep in mind that these drain, they will be of opposite phase, right? So if this is say plus V, this is going to be minus V. Yeah, because one of these outputs is called Vx, other is Vy. So we have been calling the drain of M1 as Vx, drain of M2 as Vy. So this is Vx node, this is Vy node, and they will be of opposite phase, because this point is also Vx, and y is going to be 180-degree phase shifted version of Vx. So that is why there will always be negative relation and of the same magnitude. Okay, so here we have two inductors, two capacitors, two resistors, and VDD connected to the other end of all these three. So we also noted that the DC voltage at this Vx and Vy, they are going to be VDD. So in terms of DC, all these nodes, these three nodes, they are always going to be VDD. So that means there is going to be no DC current through this resistor. And for AC purpose, where Vx is plus V and Vy is minus V, there will always be AC ground here at this common point. So what this says is basically that even if we remove this interconnect, for example, like this, then there will be no DC flowing through these two resistors, because both ends, they are still at VDD. So there is going to be no DC current through any of these resistors, even when explicit VDD is removed from the center, this common point of the resistor. And for AC, this point will continue to remain ground, because Vx and Vy, they continue to remain of same magnitude and opposite phase. Right? So there is no need to connect DC to this common point. Now for these capacitors, they are not going to allow any DC current through them, and otherwise also their other ends are also at same potential. So here also no need to connect this VDD at the common point of the capacitor. And for AC, their behavior is not going to get affected, because this will be ground, because we have plus V here and minus V here. Only for this inductor, we just need to connect it to the VDD. So that scenario remains similar to what we had earlier. So we saw that we actually need not connect VDD to the other end of all the three elements. One is enough, right? Now here, this allows us to now combine the two resistors, two capacitors, so and similarly two inductors to create another equivalent circuit like this. So we now have a single inductor which has center tapping, and the center point is connected to VDD. So for DC purpose, this is equivalent to what we have earlier. Now this inductor is equivalent of series of those two inductors. So this is 2L. And those two capacitors, they also can be combined, and it will be C by 2 because they are in series. And those two resistors, they can also be combined, and we can have a single resistor of value 2R. So here we now have a single element for R, C, and L, and then we can have our MOS in cross-coupled topology. Like this. So we have been able to make the circuit more compact, and now what we see here is that we have three elements L, C, R in parallel. So now we want to know that what will be the oscillation frequency and GM at the oscillation, and we want to carry out this analysis using a negative conductance or resistance model, because we already have three elements in parallel. So the other part of the circuit should equivalently represent minus R, not necessarily this R. So let us say minus R1, so that this will cancel out this 2R that we here have, and this C and L, they will of course neutralize each other, and on the whole, the admittance of this circuit is going to be 0, and this will act like an oscillator. So we are now revisiting this cross-couple oscillator from negative resistance point of view and find out the GM requirement for oscillation and also see that what will be the oscillation frequency. Although these two things we have already sort of derived earlier. So this one is called cross-coupled oscillator. So we are going to analyze this negative R model. So what we saw here is that we have now uh, these two MOS and rest three elements. They are very well connected in parallel, and we have two R. So what we can conclude is that this much portion of the circuit containing the MOS must be of negative R type, which will cancel out 2R. So we have to now find out what is going to be Z in or equivalently Y in, and then combine that Y in with the Y in of these three elements and set it equal to 0 to find out the oscillation requirement. So we now want to know Z in or Y in. So for that, we are going to draw the equivalent circuit of this much portion of the oscillator. And for that, we will take lambda is equal to 0. This is the assumption we will make. And initially, we will neglect parasitic capacitors of those MOS. So we have M2 here. And this is gate 2. Let us say this is the gate of the first MOS. And here we have GM1 VGS. So we want to know what will be the input impedance. So we connect Vx and find out Ix. And here we have this connection, cross connection for the drain and gate. Like this. And here we have ground. So now we know that this is Vx, this is Vy, sorry, this is capital X, and this one is small x. So we see that Vx is equal to Vx capital minus V capital Y. And this Vx is basically the voltage of gate 2. So this Vx basically becomes Vg2 and Vy is gate 1, Vg1. Since the source of these two MOS they are grounded, so we can write VGS2 minus VGS1. So this is Vx. Now if we apply a KCL at say node T1, what we get is Ix is equal to GM1 VGS1. Here this is VGS1, the second current is VGS2. So from here we can find out VGS1 as Ix by GM1. Similarly at drain 2, we see that Ix plus GM2 VGS2 is equal to 0 because both the currents they are in opposite direction. So here Ix is equal to minus GM or VGS2 is equal to minus Ix by GM2. Now we can use these VGS1 and VGS2 in this equation. So we get Vx is equal to minus Ix by GM2 minus Ix by GM1. So what we get is Vx by Ix is equal to minus GM1 plus GM2 divided by GM1 GM2. So this is Z in or Y in is minus GM1 GM2 divided by GM1 plus GM2. Now we can find out the overall admittance or the complete equivalent circuit. Circuit of the oscillator. So this will be 2L in parallel with C by 2 in parallel with 2R in parallel with another R, which is or we can simply write Y in here or Z in. So from negative resistance model, we see that the overall admittance, this Y of this should be equal to 0. So this is going to be minus J by omega 2L plus J omega C by 2 plus 1 by 2R plus Y in is equal to 0. So here we get minus 1 by omega 2L plus omega into C by 2 plus 1 by 2R and Y in we have found out. In fact, it is negative minus GM1 GM2 by GM1 plus GM2. So this should be equal to 0. That means the real and imaginary part should be equal to 0. Imaginary of Y is equal to 0 implies 1 by omega 2L plus omega dot C by 2 is equal to 0. So this is omega square is equal to 1 by 2L into C by 2. So this turns out to be same LC. So the oscillation frequency is going to be 1 by square root LC. Now real part of the admittance is equal to 0. This gives rise to 1 by 2R minus GM1 GM2 by GM1 plus GM2 is equal to 0. So this says that R should be equal to GM1 plus GM2 divided by 2 GM1 GM2. So this is what we should get. Now for identical MOS, what we will get is R should be equal to 2GM divided by 2GM square is equal to 1 by GM. So this says that GMR is equal to 1. In fact, this for general case also 2R GM1 GM2 by GM1 plus GM2 is equal to 1. So this is the oscillation condition, or GM can be found out using this equation. So we had carried out this derivation by neglecting the parasitic capacitors and found that oscillation frequency is given by this expression 1 by square root LC. So now we want to include the parasitic capacitors of the MOS and want to see that what will be the new oscillation frequency. So for a MOS, in general, there are 4 parasitic capacitors that are present. So the most common we have been using is gate to source, then between gate and drain, then from drain to bulk, and then final one is from source to bulk. So these are the 4 capacitors that are present. Let us try to include each of these 4 in the oscillator and try to see that what we get to the oscillation frequency. So now first we draw the oscillator, and then we will include these capacitors for both of the MOS. So here we have 2L, and then we have C by 2 here, and then we have R here, and now we have 2 MOS. And these MOS are grounded at the source, their source. So for each of these MOS, we are now going to include the capacitor. So first, let us include the gate to source capacitor of MOS 1. So we see that this is connected between source. So source is here, gate is here. So this gate to source basically we have CGS1, and similarly we have CGS2. So this CGS1 is basically connected here to the gate 1 or to the drain 2. So this is CGS1, and CGS2 is connected to gate 2, that means to the drain 1. So we have CGS2, and both are connected to ground, and this ground is a common like this. So we can now remove this connection from here and retain what we have shown right now. Right. So what we now get is a series combination of capacitor CGS1 and CGS2 between node Vx and Vy. And here source to bulk is going to be ineffective because source is grounded. So we need not talk about source to bulk capacitor. Now let us talk about drain to bulk capacitor. So there will be one capacitor between say drain 1 and bulk. Similarly, another capacitor between drain 2 and bulk which is grounded. Like this. Now let us talk about gate to drain capacitor. So there is going to be gate to drain capacitor, this capacitor. So here we see that since the gate 1 is connected to drain 2, that means Vy. So this capacitor is basically connected like this. In this way. So this is CDB1, which was here. So we can remove this CDB1 from here and retain it like this. Similarly, there is a capacitor between drain 2 and gate 1, but gate 2, and gate 2 is connected to drain 1. So this capacitor CDB2 gets connected like this. So we can remove CDB2 from here. Right. So we see that out of the 4 MOS capacitors, only 3 can be accommodated here. Fourth one becomes useless because the source is grounded. Out of those 3 for each of the MOS, they are drain to gate capacitor. Sorry, I have written here wrong. This is DG1, not DB1, and this is DG2. So gate to drain capacitor, they get connected in this fashion in parallel to each other, but gate to source capacitors and drain to bulk, they are basically in series, but ultimately they are also in parallel. So what we can now say is that there are going to be a number of additional parallel capacitors. So here we see that we have this scenario now, 2L, C by 2, 2R, and then we have various capacitors. Gate to drain 1, then gate to drain 2, then CGS1, CGS2, then CDB1, CDB2, and then we will have our MOS. Like this. So here we see that we have 1, 2, 3, 4 additional capacitors in parallel with the original C by 2. So their equivalent is CGD1 plus CGD2. This is equivalent to CGS1, CGS2 divided by CGS1 plus CGS2. And this is equivalent to CDB1, CDB2, DB1 plus CDB2. And these, they are going to be in parallel with rest of. So total capacitance is going to be C by 2 plus CGD1 plus CGD2 plus CGS1 CGS2 divided by CGS1 plus CGS2 CDB1 CDB2 divided by CDB1 plus CDB2. So this is going to be total capacitance. For now we can simplify it for identical MOS. C becomes equal to C by 2 plus 2 CGD plus CGS by 2 plus CDB by 2. So this is the total capacitance. Therefore, the new oscillation frequency this will be equal to 1 by square root. So here what appears is total parallel inductance, which is 2L, and total capacitance. This is omega. So this is 2L into C by 2 to CGD and CDB by 2, and then we have CGS by 2. So this becomes equal to 1 by square root of L into C plus 4 CGD plus CGS plus CDB. So here we see that we are able to include the effect of parasitic capacitors very easily. There is not much effort involved in including all the 4 parasitic capacitors. So it very rarely happens that one can include all the 4 parasitic capacitors in the analysis and yet easily derive the required result. And this is one of those rare cases where we can do this. So this was about the analysis of cross-couple oscillator for frequency and GM. Now we would like to know that when we set up this circuit, what is the maximum amplitude of the output signal that we will get. So for cross-couple oscillator, we want to know that what will be the amplitude of the output. So we saw that Vx and Vy, they will oscillate about DC value is equal to VDD. So for example, this is going to be Vx and Vy will be its 180-degree phase shifted version like this. So here Vx is going to be of say Vxp sine theta, where theta is equal to omega naught t, and Vy is going to be minus, let's say this is the amplitude, -180-degree phase shifted. And the output Vo is going to be Vx minus Vy. So this is going to be 2 Vp sine theta. So here we see that the amplitude is growing gradually, and this phenomena will continue till this amplitude becomes equal to VDD. So here we see that there is a room of value equal to VDD for these sinusoid signals to grow. So the maximum value that it can attain is equal to VDD. So here VP max possible is equal to VDD. Therefore, V out max that we can get is 2 VDD. So the amplitude maximum amplitude possible is equal to 2 VDD. Now, if you talk about peak to peak amplitude, then this is going to be 4 VDD. So here in this version, what we had done is that we had fixed the source to a fixed value, 0 voltage to ground. But here, all these currents, ID1 and ID2, they are free to be anything determined by these voltages, gate voltages. So here, voltage is restricted. Common source voltage has to be equal to 0 volt, but their drain currents, they are free to have independently any value determined by the X and Y or the output. But now we can have another version of this oscillator where the current, their sum is going to be fixed, determined, but the source voltage is free. So this is called tail biased Crosscouple oscillator. So in this case, we have everything else same. C, R, all these things are same as the earlier case. Most interconnections are also similar in the cross-couple fashion, like this. But instead of keeping their source fixed to voltage, for example, 0 volt, we keep it free and connect it to a constant current source. So now here you can see that sum of these two currents, they have to be fixed. So ID1 plus ID2, this will always be equal to ISS. But now this VS is free. So this will not be at 0 volt or any constant voltage. So there will be a fixed DC voltage. But for the AC voltage, VS is of course going to be 0 because these two sources or the two drain voltages, VX, they are always of same magnitude and opposite phase. So AC part is going to be 0, but now VS can change based upon any other fluctuation. Yeah. So this will contain both DC and AC. Both will contain DC and AC. So DC part, so for DC drain current, what we will have is ID1 plus ID2 is equal to ISS, and they are going to be identical. So this will be 2 ID is equal to ISS, implies that the DC drain current that will flow is going to be ISS by 2 of them. Now here also the oscillation frequency is going to be total L and total C, so it is going to be given by same formula. But now as these inputs they start growing, what will happen is these drain currents they will also start increasing, and when these X and Y outputs they become very large, what will happen is one of the MOS will be fully opened and other will be almost short circuited. That means one of them will be like on switch, other will be like off switch. So for large values of these Vx and Vy, they will start acting like a switch. And Vx and Vy, they will inevitably will become a large. So what will be consequence that entire ISS will be flowing through one of these MOS. So at these moments, M1 is on, and at the same moment, M2 is going to be off. So these drain currents, ID1 and ID2, they will become square wave. So their waveform is equivalently going to be like this. So if ID1 is like this, ID2 will be its complement. So we know that these currents, they contain various harmonics. So there are various currents flowing through these drain. So this is ID1, ID2. So now what happens here is that for the fundamental current, this path is going to be open. So for the fundamental, the equivalent circuit is going to be the circuit is like this. So this L and C, they behave like open circuit, only resistor part is there here. So the fundamental of this ID1 and ID2, they flow through this resistor. So this is ID1 and ID2 is 180 degree shifted version. So ID2 is going to be negative of this. So this Vx is going to be minus R into I1, where I1 is fundamental of ID1. And fundamental here we can see is ISS into 2 pi cos theta. So this is minus R 2 ISS by pi cos theta, and theta is omega naught t. So this is Vx. Now Vy is going to be minus R into I1 of ID2. So this is of ID1. And this one is 180 degree shifted version. So this is going to be negative of that. That means R 2 ISS by pi cos theta. So therefore, the output is going to be Vx minus Vy. So this will be minus 4R ISS by pi cos theta. So for this case, when the source voltage is free, but the total drain current are fixed, so the output amplitude is equal to 4 ISS R by pi. So we see that we have a different amplitude of the output possible from the oscillator based upon whether it is a voltage fixed version or whether it is a current fixed version. So these are the two versions possible for this cross-coupled oscillator.